Okay, this is lecture 8 of the course Electrical Systems in Agricultural and Biosystems Engineering. The previous topic was on renewable energy sources for power generation or electricity generation. And the last discussion was on solar power. Now, this new topic or new lecture will be a continuation of that, particularly solar. And this is to show, okay, the objective of this is to transition into the next topic of biomass and biofuels. And the um, figure 1, as shown, is just the start of that. Okay, we have a diagram, a schematic showing the influence of solar power to the um, energy cycle of the Earth. This cycle is incomplete, but to show the influence of the sun to the energy cycle, the diagram is shown to reflect, okay, the overall influence of the sun to the different energy sources used, okay, as power, to generate power. So the sun, okay, it actually heats up the Earth via its solar radiation, okay, and this is referred to as the total solar radiation, with its irradiance in the units watts per m squared. This drawing is not drawn to scale. An important factor in the total solar radiation is the total available value of solar radiation available to the Earth, and it's actually 1363 watts per m squared. This is the solar constant. Now, this value varies depending on literature, but this is a a constant that is generic in the solutions to solar engineering research and computations. Now, the reason for this differences in values is because at the macro scale, it's very difficult to measure these amounts of energy or energy transfers, okay, and transformations. So let's start looking at this process or this diagram and um, looking at it in detail. We see the sun, okay, the heat of the sun by the solar radiation affecting first the atmosphere and the waters of the Earth. Heating up the atmosphere, it generates well the two sources of energy via the wind and the ocean wave. There's already discussion on the wind energy. About the ocean wave, this is a rather new technology, although there's been development since the 1950s, and we have, or there is the continuous development of this in somewhere in Great Britain or United Kingdom. So energy, okay, via the heating up of the atmosphere results to these waves, okay, the wind and the waves. Another effect of heating up the waters of the Earth is the results to the hydrologic cycle. So heating up results to evaporation, also transpiration. So it's evapotranspiration, thereby leading to the stream networks that we have, and this stream networks eventually give rise to the power source of hydropower, okay, via the streams and rivers and the dams that are constructed along these rivers. Next up is the influence of the sun to a very important process in the in biological um, in biology, this is in plants and it's called photosynthesis. This gives rise to the energy that is referred to as biomass and also the biofuels. Okay, those are harnessed from the uh, carbon-based materials of uh, plants and well, if ever that would include animals as well. But eventually, okay, when the biomass and biomass of plants or the plants themselves get compacted through time, okay, and with pressure and heat, okay, across geologic timescales, this eventually become petroleum that is now powering the conventional uh, sources, okay, or the power from conventional sources. So eventually, or technically, petroleum is biomass. Okay, it's just the reconfiguration of the carbon atoms in the plants. In fact, Amory Lovins, a physicist, calls oil or petroleum primeval plant goo. Okay. Now, besides this, those absorbed by the Earth, okay, the heat, the solar radiation absorbed by the Earth. There's also the direct beam and or the use of the solar radiation by the direct beam and diffused radiation, and this leads to the photovoltaics, which was already discussed. And then you have also there's also the solar thermal or direct use of solar radiation to heat up facilities such as what water heaters and even greenhouses. Now there's also this recently developed technology on ocean thermal energy, or technically it's OTEC or ocean thermal energy conversion. And then besides this, there's the reflected radiation, which is just the heat dissipated back to space. Now, before the discussion moves over to biomass and biofuels, we or there's a sample computation to the previous topic on the photovoltaics. And the problem is on the determination of or the number of photovoltaic modules needed to service a given electrical load for a small home, as shown, okay, in the table, and in a given location, that is Pili, Camarines Sur. Now, to start off with this problem, okay, the table shows the daily usage, and this is just approximated, okay, and the rated wattage, the power consumption for each appliance. Okay, so the load here are the appliances, and there is a daily use multiplied to the wattage, which eventually results to the energy consumption in watt hours. So R times watts equals watt hour. Again, these are approximated uh, in the daily use of the equipment or the appliance. And eventually, this would give rise to a value that is the total requirement for that small home. All right, so let's look at now let's try to solve this one. Let's start with solving or identifying the requirements. Let's see first what are required. We're asked to determine the number of panels. So given our, sorry, what happened? Okay, given our Apologies for the inconvenience. I am having issues here. Okay. Okay, given we have the appliance and lighting load, and then we are asked to determine the number of panels. Now there's a caveat here. Okay, the number of panels is or changes depending on the type of the system. If it's grid tied or standalone, or what other refers to as off grid. Now, so we will be discussing this both, or determining this both. We have here the B, and then we have to find this two, and we start off with determining the latitude and the longitude, or the coordinates for determine coordinates. Okay, let's try to solve this logically. Okay, determine coordinates, and needed here is a map. Okay, so for Pili Camarines Sur, this is a town or municipality south of Metro Manila. I think it's around 400 kilometers away. Okay, this is 13 degrees for 34, sorry, 34 minutes and 51.9 seconds in latitude, and in longitude 123 degrees, 15 minutes, 46.39 seconds. Once we have that, okay, we have to determine the incident radiation. That is the direct solar radiation. Now, there are solutions where it can be determined from formulae, okay, based on solar engineering principles. But here, what's going to be done is to look it up in a data sheet that's available. Okay, with regards to the solar radiation, it actually varies depending on the location. So it's the geographical position, and then also the latitude, and also on the azimuth and the time of the day. Now here again, we're going to look up the data from a data available source. Okay, that's a database. Let's look at this data sheet that we have on the solar, the direct solar. Okay, and this is a geospatial database, okay, for the whole Philippines. And when you check or tick the direct solar, it shows the data for the whole Philippines at I think the This is on a 1,000 kilo 1,000 meters by 1,000 meters. Is it correct? Or I think it's if 1,000 kilometers, that's going to be 10 kilometers. So I think this is more than 10 kilometers, one size. But anyway, so let's forgo that. What we do is we identify the point where that would be. Okay, the 13 degrees, 1, 2, 3 degrees. Okay, 13, 34. I think it's going to be here. 59, 52. Okay, 51, 24, and then we have 1, 2, 3, 15. So I think there's not really that much difference to identify or get the exact point where the coordinates lead to, but I think we can already click here so that we see the location for or the identify the place as PD, and then get the average kilowatt hour per m squared per day for this location. So this is the average at 395, and then yeah, we have the monthly data as well. So let's go back to our computation, and then we have the direct solarization as 3.95 from table from database. Direct solarization. Okay, let's try to identify it as RD is equal to 3.95 kilowatt hours per m squared per day. Now we have to determine the sun peak hours. The peak sun hours. And that is actually determined by the same, value that we already derive or determined from the database. So actually, the peak sun hours, let's try to identify it as peak sun hours or SH is equal to what? 3.95 hours. Why is that? Because actually this means, okay, this actually means that let's use this one for, okay, so let's organize the thought. So we have 1 kilowatt hour, 1 kilowatt for 1 meter squared per day is incident or for 3.95 hours. That is the other understanding or interpretation for that. So we have the SH now as 3.95 hours, or let's rewrite it as R or H, just H. Okay. Now what we do next is to determine the power requirement for our location. Set it as P, and the power requirement is actually just the energy requirement over the peak sun hours, and it's equal to what? It's the E is 1,506 okay, watt hours over sun hours, which is 3.95, okay, hours, and this will cancel. Eventually, P will just be left with um, the wattage, and let's try to compute for that. Okay, that is right 1506. Is it really 1506? 3.95. Okay, 381. It's 381 watts. Okay, once we have the power, we can now determine the number of panels that we need. But first, okay, we have to set a a rating for the panel, and also some configuration considerations such as the safety factor and the efficiency of the system. So determine, okay, let's just set module rating, the and set up requirements. And we have the module rating. We see that this is R equals, let's say one panel or one module is 260 watts. And then we identify a safety factor. SF equals 20%. And then the efficiency of the system, let's write it as EFF at 80%. So we get now, okay, after this, the result for the number of panels. Okay, so the number of panels is N, and N is simply the P over the module rating R multiplied by the safety factor. So 1 plus 0.2, or let's first set up the equation, SF all over the efficiency. And this, when you plug in the values, okay, P is how much is that? 381. Okay, 381 watts over the module rating of 260 watts. So eventually this will cancel out, multiplied by the safety factor and the efficiency. And the value will lead, or the numbers will yield N equals what? Let's try to compute. Okay, 81 divided by 260 times 1.2 divided by 0.8. Okay, that's 2.19. Unfortunately, you won't be able to get a fraction of a module or a panel. So rounding up, okay, this is 3. So 3 panels needed. This is for a grid-tied system. Now for an off-grid system, okay, what should be done is to now look into the details of the direct solarization and determine the smallest value, and that would be 3.16 for the month of July. Okay. Now, this same value will now be used to solve for the, okay, so lowest, okay, determine. So we started out with the determination of the location, and then what we'll do is go back, okay, go back to this portion of the solution, okay, determine the peaks and hours, and we did for the least, okay, determine the peaks and hours for the lowest, okay. Okay, what we first do is determine smallest peak, that's smallest the peak, sun hours, and that is what we have. SH equals 3.16 kilowatt hours per m squared per day. And we continue again solving for our n using the same steps. Okay, I'll forgo the notations, okay, before solutions. So I'll just proceed with the solutions. Okay, what we will do is we determine the P. Okay, 1506 kilowatt watts. Okay, that's 3.95. Okay, this is, sorry, this is the peaks and hours is no longer in these units. I'm sorry, apologies for that. Okay, let's just remove it. This is just 3.16 hours. Okay, 3.16 hours. And we compute for the P by dividing the E, or the total energy requirement, which is 1506 watt hours by 3.16 hours, and we get the value. This time it's actually what? It's 476, okay, watts, and 476 watts will be, okay, just multiplied or divided by the 260 and multiplied by 1.2 over 0.8, and we get the value of 2.75, and is approximately 3. Okay. And that is the final answer. So it's the same to the grid tied. So 3 panels is enough to supply the requirements for a system that is off-grid using the same loads. So it means this panels setup is already enough to supply for 1 year, or for the daily requirements for the rest of the year. Now, the solar, again, you would need to have a well, if you were going to do this, okay, so you have 3 panels. That's 260 watts each, and you have to connect them in series. Okay. Okay. This is the schematic for your solar. Sorry. And then you connect this to your circuit breaker. sorry, not the overload breaker. Okay, and then the breaker is connected to your charge controller. Let's just write here MPPT. That is the most common charge controller. The charge controller is connected to the battery. Okay, or let's just use the traditional battery setup. Anyway, let's just put the battery over here. Whatever it could be a 12-volt battery. How many that would influence the number of, or the size of the MPPT. Now this is connected also to the you have here the inverter before it gets to your branch circuit, okay, in your to your set or to your appliance circuit, okay, or lighting load circuit. Okay, so to determine the MPPT, okay, what needs to be done is to just multiply the number of modules, okay, by the load, okay, 260 watts times 3, that's going to be 780 probably, yeah. And then okay, okay, sorry, okay, the 780 you now divide by the voltage of the battery, okay. If it's 12 volts and you have a factor of one, at least 10% safety factor, this would result to, I think it's, let's see, 780 divided by 12 times 1.1, it's 71.5, and this is approximately probably 75 amperes. So you get a 75 ampere 12-volt DC MPPT. Now for the inverter, it's actually just the total load. Okay, let's see the total load, but not the daily load. Okay, not this one. We're going to look at this one. Okay, at one time. Okay, at one time of the day. Probably you might be using all of them at the same time, so you just add them up, and this is actually what 25 plus 60 plus 27 times or plus 1000 plus 30 is 1142. Okay, 1142 watts. And to determine the inverter, so you just 1142 watts, divide this by the oh sorry, you don't have to divide this, you just round this up. Okay, so you probably will need 1200 watts for a specific inverter, okay, to supply at one time your demands. It's the water heater, okay, that's consuming a lot of energy at any given time. Right, so there's an alternative solution to your this one, and it's actually just to determine the peak month of consumption and compute the daily consumption in kilowatt hours for the peak month of consumption. Okay, and then divide this daily consumption in kilowatt hours by for the month by the average peak sun hours, and then continue the solution as with the step A or step 1, okay, in step A, in number or letter A. Okay, all right, so let's proceed back to the discussion where we are going to tackle the biomass. But actually, it's just a presentation of the heating value of biomass. Okay. Now, this is the value that's very important in determining um, the capacity for a certain um, um, power plant, and that's running on uh, biomass or biofuel. The generation of power in these kinds of plants are very much the same to how the conventional uh, power sources are being used. So you have gasoline, diesel, natural gas, and bunker fuel. Okay, the same with this the utilization of this biomass for power generation. There's the burning of the fuel in a furnace, and then a water or a fluid, usually water, is evaporated to generate steam, and that steam is directed towards a turbine, and then runs this turbine that is connected to a shaft, which with that shaft generating power via the generator. Okay. Now in the table, okay, shown are actually chemicals, and mostly are well, the conventional power sources such as gasoline, diesel, and to the right are the nuclear power sources and the biomass themselves. And one can see immediately from the data, because we have here the data for nuclear in gigajoules per kilogram. You can see how dense the energy is in these kinds of fuels. Even the uh, for that, or the energy um, for the conventional ones are even a lot higher than the biomass. They are considerably lower, okay, in heating value per kilogram. Well, except for the low quality coal, okay, as shown in the second to the last, okay, or the last one, okay, the lignite or the brown coal. Okay, these are low quality coal. And increasing the operating temperature of coal likewise increases the heating value. Okay. Another thing with biomass is the density. Okay, so not just the energy density, it's just the physical density. A kilogram of rice hull, for example, takes up space for 6 times that of the space for gasoline. Okay, for an equivalent weight. Okay, and so I think there's a lot of potential that can be made in this category, okay, in terms of the research of the AB engineering profession. So that would be all for power generation. The next discussion, the focus would be on um, um, the generation and distribution. But before the discussion is ended, okay, we have here a presentation on the completion of the energy cycle earlier shown, okay, just to show the complete energy balance, but not in figure and not in values, but just in concepts. Okay, now there's the energy from the gravitational effects of the sun and the moon. Okay, and this leads to what? The ocean tides. Okay, and there's also the energy from underground, okay, or under the earth, resulting, actually these are from earth sciences, these are energy resulting from the Big Bang that's already stored there, okay, and they are in the forms of geothermal and nuclear energy. So you have the energy from, or the heat from the core of the earth, harnessed via geothermal power plants. And then the nuclear, you have the radioactive isotopes mined from under the earth, okay, or synthesized from in laboratories, if ever, but still coming from naturally occurring elements. Okay, so that's all, and thank you again for listening.